Hello, I'm Tana, your MLC tutor. Okay, in this video, I'm doing a problem, again out of my ASM study manual, on a non-homogeneous Poisson process. So really that just means that the rate at which events occur is not constant, it varies with time. So your lambda will be a function instead of a constant. In this problem, they tell us that trains arrive in a Poisson process at a rate of 10 root t per hour. So I just said the number of trains per hour follows a Poisson distribution with lambda of t, so this is your intensity function, or the rate at which events occur. Varies with time. They said it's 10 root t. I call that 10 t to the 1/2. And they tell us that t is the time since 7 a.m. They want us to calculate the 90th percentile of the time of the first train arrival after 7 a.m. So, I know, and I'm calling t sub 1 the time until the first arrival. We want the 90th percentile of that, right? Yes. Okay, so I know some things about how this time until the first arrival is distributed. I know that since the number of trains per hour follows a Poisson distribution, I know that the time until the first train arrival is going to be exponentially distributed. Okay, so if I want to calculate the 90th percentile of this variable, and I know that it follows an exponential distribution, all I have to do is set either the cumulative distribution function equal to 0.9, or 90%, or the 90th percentile, or the survival distribution equal to 0.1. So we can either do cumulative distribution function for the time until the first arrival at some value, which we're trying to find, this will be the 90th percentile, is 0.9. Or we can do the survival distribution for the time until the first arrival, evaluated at our 90th percentile, will give us 0.1, because 10% are above the 90th percentile, 90% are below the 90th percentile. I'm going to use the survival probability, the survival function, because I think that's easier and quicker. So I know that this is e to the negative lambda. Here we're going to have to integrate over our time interval, which is 0 to x, the intensity function, which is 10t to the 1/2 dt. And I talked about this in more detail in another video, but the reason we're integrating from 0 to x, what we're really looking at here is the survival function evaluated at x is the probability that the time until the first arrival is greater than x. So that's no events happen on the interval from 0 to x. So the probability of no events, if your number of events follows a Poisson distribution, is e to the negative lambda, is what we're doing here, or e to the negative integral of the intensity function. And we're going from 0 to x because we want the probability of no events on that interval. Okay, so really this is it. You'll solve for x. That'll be your 90th percentile for the time until the first arrival, and then they want to know the amount of time since 7 a.m. So that'll be in terms of hours, and you'll add that to 7 a.m. I'll go through with the integration for anyone who isn't comfortable with it. Okay, so for anyone who is interested, this is my integration. Skipped a few steps, but just in case you need to check your work or something. So we're looking to set the survival function for the time until the first arrival equal to 0.1. So then this x is going to give us our 90th percentile. When I went through all of that and solved for x, I got 0.4293. So we were looking at the number of events per hour. So we expect about 0.4293 of an hour until the next event. I think it was train arrival. So, and we want to know this was starting at 7 a.m. We just want to know the time of the first train arrival, the 90th percentile of the time of the first train arrival. So 7 a.m. plus 0.4293 of an hour gave me 7:29:54, or about 7:30. All right, I hope that was helpful and happy studying.